So this video is on salts. Now, the first thing we should do is define salt. A salt is something that is ionic, which means it consists of a cation and an anion. Now, some salts are neutral, some are basic, and some are acidic. If they are neutral salts, they will lead to a pH equal to 7 as long as we're at 25 degrees Celsius. All right? So let's talk about some neutral salts. And the way you want to talk about it is you want to think about the anions and the cations and how they're going to behave. Really important point, by the way. Okay, just to remind you, this is going to come up over pH is about this. Not the acid, it's about the H2O plus concentration. Or it's about the hydroxide concentration. Okay, let's start with our strong acid. We have strong acid, hydrochloric acid. So this is one of our acids. It's a strong one. Okay, the Ka for this reaction is very large. And what that means is the equilibrium point is way over here on the right. Now, even though we could consider this chloride to be a conjugate base, we know there's very little reverse reaction. Like there's not even a numeric value for this. It's just listed as large, which means even though theoretically this happens, it really kind of doesn't. And what that means that the chloride ion is not going to react with water and grab a bunch of hydrogens from it. Okay, so if I just throw some Cl minuses in the water, they're not going to react with the water. This is not going to happen. Okay, that's just not going to happen. So anions can sometimes do that. They can grab hydrogens from water, but not if they are the conjugate of a strong acid. So which anions are neutral? Okay, the anions that are neutral are the chlorides, the iodides, the bromides, the nitrates, the chlorates, and the perchlorates. Now, anions can be bases, okay, but not these. Okay? Cations can sometimes be acids, but not the ones that come from strong bases. And strong bases are the metal hydroxides that are either group 1, strontium, or barium. You must memorize that. So that means Na, K, Li, cesium, I'm missing one, rubidium, I think, that might be it. And also barium and strontium. Those guys are not going to have an effect on the pH because they're not going to behave as acids. Okay? We'll see that in a few minutes when things can act as acids. All right, so an ionic compound like lithium bromide will be neutral because neither one of these guys in here, neither the cation nor the anion, okay, they're both the conjugates of strong acids and bases respectively, and therefore they will have no effect on the pH. Let's talk about when the pH will be affected. So let's say you have a salt. Now this is a basic salt, sodium acetate. Now how do I know sodium acetate is a basic salt? This is why. Because I know the acetate ion is the conjugate of acetic acid. Right? That's got a Ka of 1.8 times 10 to the minus 5, right? So acetic acid will react with water to make the acetate ion, right? Plus H3O pluses, right? Now, again, I'm just going with the little L there, right? And what this is the acid, and this is its conjugate base. Now, we know of the two bases in this equation, the acetate ion is a stronger base than the water is, right? Because we know with a value like this, equilibrium is all the way to the left. Most of these vinegar molecules are going to remain intact. They're going to stay. So if I have a beaker filled with this, it's mostly filled with the acid that's unionized. And there's a few H pluses, a few A minuses in there, and that's it. Now, that means that this guy right here likes to grab hydrogens. All right? It likes to behave like a base. And it's a stronger base than water, so when it gets into water, what will happen is this. It will react with the water. And when it does this, it'll grab that hydrogen back. And what you want to notice is, right, even though we're forming this, what's really important here, okay, is that we're making these. Okay? Make sure we're clear. This always messes up soon. It's not the presence of the acid. It's how the hydronium or hydroxide concentration is affected. the addition of the acetate ion is going to increase the concentration of hydroxide, and that is why it is a basic anion. It does not have to do with the formation of this. Yes, we're going to form acetic acid, but what's more important is we're increasing the concentration of hydroxides when we put the acetate ion in there. Now I'm going to show you a little bit of math hocus pocus, because what I want to do is get the pH for this solution. Watch it very carefully while I show this one time. What I'm going to do is write out the Ka for the top equation, and then I'm going to write out the Kb for the bottom equation. And then what I'm going to do is going to add the two equations together. Ready? Here we go. So, the Ka is basically HC2H3O2. Oh, that's on the bottom. Sorry, I can do that, right? And then the top is going to be the H3O plus times the C2H3O2. Now that's equal to the Ka. Everybody should be okay with that. That's the Ka, right? Now I'm going to add these two equations together, right? And when I add the two equations together, remember we multiply the equilibrium expressions. Remember that, right? So if we add equilibrium expressions, we multiply the equilibrium. If we add equations, the equilibrium expression will be the multiple of two KQ equations. So I'm going to multiply that times the Kb for the second equation, which is like a base. And this goes like this. I've got on the top here HC2H3O2 times OH minus over C2H3O2 minus. All right, bad bracket over there. Okay, if I add these guys up, okay, now the water stays, but the water's never in there, so I'm just going to act like the water doesn't exist and ignore it. See how I've got this over here and this over here, and this over here and this over here? When I multiply these guys out, what I basically get is, what's left is H2O plus H2O yields H3O plus OH minus. Or if you want to look at it this way, this cancels out this cancels out this, and I basically get H3O plus times OH minus. Or the Ka times the Kb. Now be clear, the Ka of an acid times the Kb of its conjugate base is equal to the autoionization of water, which is just Kw, which is just 10 to the minus 14. So here's a really simple idea. If you have a Ka for an acid, you can figure out the Kb for the base, and therefore you can figure out the pH, like so. So here's our original problem again, right? Now don't forget, the Ka was equal to 1.8 times 10 to the minus 5. We have a 0.10 molar solution of sodium acetate. Now the sodium ion is neutral, so we don't even care about that one. What we do know is this acetate ion is going to go in there and create some hydroxide. And yes, it's going to create some acid, but that doesn't really matter. What's important is how are we affecting the hydronium or the hydroxide concentration. That's what's critical, right? So now we do this problem. We do 1.8 times 10 to the minus 5 times Kb is equal to 10 to the minus 14, based upon, because Ka times Kb equals Kw. And then we do a little math work here. I'm going to pause because I didn't do my math. So when we do the math here, we get that the Kb, I don't know that happened. We get that the Kb is equal to 5.55 times 10 to the minus 10. All right, here we go. Well, we're back to the same problem, aren't we now? We have 5.5 times 10 to the minus 10 equals the base concentration, which is 0.10, minus X over, okay, the OH minus concentration times the HC2H3O2 concentration, which is basically equal to X squared, approximately equal to X squared over 0.10. And then we can just do the math and solve for X. And now make sure we're clear. X is going to be the hydroxide concentration, isn't it? So the concentration of hydroxides and also the concentration of acetic acid ions is 7.45 times 10 to the minus 6. Now make sure we're clear. This number is far less than 0.1, so therefore we definitely are good with the 5% rule. We could check that if we want to on the AP, we should. But the other thing I want you to recognize, even though we've made some of this, the amount of that we made is much smaller, several orders of magnitude smaller than the concentration of the acetate ions. Okay? And this is why the acetate ions are the ones that are really truly affecting the pH here. Now this is equal to the hydroxide concentration, So we can take this value that we have here, okay, point, right? And we get 5.12 when we take the negative log of this, right? Now that's equal to the pOH, which means our pH is equal to 8.87. Now, again, let's make sure we're clear about that. That's a slightly basic pH, right? And that's what we would expect. Now, we can do the same thing with another salt. Now, this salt is different. We have the following ions here. We have a chloride in it, and we have the ammonium. Now, the ammonium is the conjugate of NH3, right? The Kb of ammonia is 1.8 times 10 to the minus 5. It just happens to be the exact same thing as the Ka for vinegar. Okay, so the math here will be similar, right? Now, what's important is here you have two ions in this salt. You have this one, and that one is neutral. But we have this one here, which will be acidic, right? Cations can be acidic, essentially, right? Somehow they're going to either add hydroniums or absorb hydroxides, one or the other. Metals will absorb hydroxides. Nitrogenous the conjugates of nitrogenous bases like ammonium have hydroniums to give up. So we have 0.0200 molar solution of this, and the reality is the math is going to be almost exactly the same, right? Because what we're going to have is our Kb is going to be the NH4 concentration on the bottom, right? On the top here, we're going to have the NH3 concentration, which is a base, but again, we're going to have a lot less of that than we have ammoniums, and then we're going to have the H3O pluses here on the top. Now again, we have the same form. This is going to be very useful, right? If we know the Kb for the base, we can figure out what the the Kb, we can figure out what the Ka is. That's what we're doing here, right? This is the Ka because we're adding acidic salt, right? And the Ka for that is going to be equal to 5.55 times 10 to the, let me go back and look, times 10 to the minus 10. And I did that by substituting this into there and getting the Ka. So this value is equal to 5.55 times 10 to the minus 10. And we get the same exact thing. I mean, we can do an ice table, right? I mean, this is starting at 0.020. It's going to go down by x. These are going to go up by x, right? But we do the same. We have x squared on the top. We have 0.020 minus x equals 5.55 times 10 to the minus 10. And make sure we're clear, when we get x is going to be equal to the H3O plus concentration, so we can figure out what the pH is. And again, I'm going to do the math real quick on my calculator. And so we get an x value of 3.32 times 10 to the minus 6. We can take the negative log of that, and when we take the negative log of that value of the 3.32 times 10 to the minus 6, we get a value of 5.47, which is the pH in this particular case, because the X is the hydronium concentration. It's this right here in our equation. And then we can figure out the pOH and everything else like that. Notice it is an acidic pH. All right. We'll talk more later.